solving trig equations again, only now they're getting a little fancy with the domains, which doesn't really change anything for the first several steps. Our first procedure is still isolate the trig function. So if you have 2 sine x minus root 2, that means 2 sine x equals root 2. And then you divide by 2 and you get sine x equals root 2 over 2 or 1 over root 2, whichever you're familiar with. I'm used to the second one. I know the first one is technically better because it's got a rationalized denominator, but either one. It's good if you can recognize both. So this question is asking us, what angles are we at if the sine function is at 1 over root 2? Well, we're definitely not down here. In quadrants 3 and 4, sine is negative, and this is a positive value, so that's definitely out. We must be in either quadrant 1 or quadrant 2. Those are the ones where sine is positive. And sine is opposite over hypotenuse. So we're looking at triangles where the opposite side is 1. There we go. And the hypotenuse is root 2. Does that look familiar? It's one of our special triangles. And you probably have figured out that this side should be 1 and this side should be negative 1. That's what memorizing the special triangles does. This is the 45-45 triangle, just oriented differently in each of these cases. And if that's a 45-degree angle, and this is also a 45-degree angle, that's enough for us to figure out the solutions to this problem. Let's switch colors here. The actual solutions, or the standard angles, are measured starting from 0 and going counterclockwise. This one's easy. This one really is 45 degrees. Quadrant 1 is nice that way. This angle is a little less obvious. It's 135 degrees. I think of it as you go all the way around to 180, and then you go, too far, back up 45 degrees. And that gets you to 135. So from that, it looks like our solutions should be 45 and 135. But those aren't the solutions because they've given us an unusual domain here. They say, we want solutions that are between 360 and 720 degrees. Neither of these qualifies. Okay, well, where's our next solutions? This 45-degree solution will happen again 360 degrees later, which will put us at 405. Hey, that one counts. That's in the range they specified, so 405 is a keeper. What if we go forward again? If you add 360 to this, you get 765 degrees. That's too high. So if you considered this, that's excellent, but it turns out you went a little too far and you got outside domain again. So 405 is the only valid solution we get from there. 135, if you add 360 degrees to it, becomes 495. That's part of our solution. It's in the domain they specified. And 495 plus another 360 will be 855 degrees too high. So the solutions they were after here were 405 and 495 degrees. Let's do that again with radians and see how we do there. Root 3 cotan x plus 1 equals 0. That means root 3 cotan x equals negative 1. Divide by root 3 and you get cotangent x equals minus 1 over root 3. Now, I don't have any SOHCAHTOA kind of ratios memorized for the cofunctions or the reciprocal functions, so I'd rather not work with cotangent. Quick way to fix that, if you flip this left side, the reciprocal of cotangent is tangent x. You can do that as long as you also flip the right side, which gives you minus root 3 over 1. So, where are we if the tangent function is at minus root 3? Well, we're not here. Tan's positive in that quadrant. We're not here either. Tan's positive in that quadrant. We must be either there or there. You remember tan is opposite over adjacent. So our opposite sides must be root 3's and our adjacent sides must be 1's. So we'll have something like this. Opposite side is minus root 3, adjacent side is 1. Here, opposite side is root 3, adjacent side is minus 1. How did I know where to put the negative signs? Well, this is a measurement in the x direction. It's a positive x, so it should be plus 1. This is a measurement in the y direction, so it should be negative. So right and down means positive and negative. In this quadrant, left and up corresponds to negative and positive. So again, do you recognize these triangles? They've got root 3 in them. They've got 1. You might remember that you've seen a triangle with a 2 that looked like these. And sure enough, this is the 30-60 triangle again, only this time the 60s are the reference angles. So we have 60 in this corner, 60 in this corner. Sorry, this is cramped. I'm trying to work in the space they gave us on the page, and it isn't a heck of a lot. So for general solutions, starting here, 0, 90, what angle is that? It looks like it's 180 degrees, and then back up 60 degrees, so 120. Oh, and I do this every time. I just realized we're supposed to be in radians, so forgive me. This 60 degrees should be pi by 3. This 60 degrees should be pi by 3. And when I said 120 degrees here, I meant 2 pi by 3. And for this last angle, pi by 2, pi, 3 pi by 2, this angle is going to be 2 pi minus pi by 3. So 5 pi by 3. Those are our two solutions. Right about here where we have more space. 2 pi by 3 and 5 pi by 3. Are those valid? Nope. They want solutions in this narrow band, which is actually negative angles, and so both of these are no good. They're both higher than 0. Adding 2 pi is not going to help us either, so we have to go in the opposite direction. If we subtract 2 pi from each of these, let's see where that gets us. 2 pi by 3 minus 2 pi is the same as 2 pi by 3 minus, I'll write this out. That's 2 pi by 3 minus 6 pi by 3. So this is minus 4 pi by 3. Even that is no good. It's lower than pi, so it looks like this solution is a total bust. 2 pi by 3 is too high, minus 4 pi by 3 is too low, so we junk that one. 5 pi by 3 minus 2 pi is, this is our last chance to get something here, 5 pi by 3 minus 6 pi by 3 is minus pi by 3. There we go. This is minus a third pi. That falls in the domain that they indicated. So in this case, though in theory we had an infinite number of solutions from here, only one of them was in the domain that they wanted, minus pi by 3.